Hello everyone, my name is Stefano. I'm the head of automotive here at Embotech AG.
Hello, I'm Sandro Merkli. I also work at Embotech. I'm a software engineer.
So Embotech is a spin-off company from ETH Zurich, and we specialize on autonomous decision making. The next series of talk are delivered for the Autoware Foundation, the Autoware Academy in particular. We're going to be talking about autonomous decision making for the purpose of autonomous driving, and probably the focus is going to be more on motion planning, which is really our area of expertise. So I'm going to start with the first series of talk, giving a broad overview of what decision making is in autonomous driving and what motion planning is. And the last talk is going to be delivered by Sandro.
Yes, I will talk about the open motion planner that we are going to contribute to Autoware. I'm going to show you how to use it, what it does, and what the results look like. So now there's going to be the first lectures by you, Stefano, and I will excuse myself until my lecture.
Fantastic, I'll see you all later. Hello again. This is going to be the first one of a series of short videos developed and prepared for the Autoware Academy. In this first video, I'm going to discuss the hierarchical architecture in autonomous driving. So I'm going to show you a very broad overview of where the various components in the autonomous driving software stack fit and how they fit together. What I'm going to present you is what I believe is the de facto standard applied both in industry and in academia. I don't think that this is necessarily the way autonomous driving software will be structured and will be developed, but it's a good enough architecture that will give me a good framework to where I can then discuss various algorithms and various way of developing the different part, and in particular the decision-making part of the software stack. Okay, so in order to present and show you the full architecture, I think it would be worth to start from the vehicle itself. That's the piece of hardware, the chassis and the four wheels, if we're talking about a standard vehicle. Normally from this vehicle we require measurements, and this could be all sorts of things coming from a more traditional sensor to the new type of sensors. And people often divide sensor into kind of three categories. They call it the 1D, 2D and 3D sensors. So 1D sensors being, for example, wheel speed or accelerometers, 2D sensors being cameras, and 3D sensors being LiDARs. So these are all the kind of information that are needed and are fed into what is often called the sensor fusion stack. So sensor fusion, localization, and state estimation are all important information that are derived from the raw information sensor itself. This information might be augmented by other information like maps, whether are HD maps or any sort of preloaded offline information, and all of this is what is normally called the perception layer of the autonomous vehicle software stack. So this is the perception. Now, once we have the perception information ready, we can then plan some navigation. So this could be a long-term route planning. Navigation together with sensor fusion, localization, and estimation will give rise to the behavioral planning of actually how the vehicle is gonna make certain decisions. From the sensor fusion, the perception layer, we can also do estimates on how other users are going to move in the environment. So how obstacles, like whether it's other vehicles or pedestrians, are going to participate, and they're going to make prediction on how they're going to move in the future. And all this information together with the vehicle state estimation. So state, remember that estimation is those things that we don't measure directly, but we estimate, we infer from other measurements, and also together with the drivable space and the high-level plan and the dynamical obstacle prediction, and going all fit together in what we call the motion planner. So the motion planner is the decision-making part that actually and eventually decide how the vehicle is going to move. Again, I'm going to show a lot more details later on. And this is what we call the decision-making part of the motion planner. So decision-making is not just the motion planner, but it's also the prediction of the participant, the behavioral planning, and the navigation itself. The motion planning output is actually a detailed plan of how the vehicle will move. We will see later that there actually are two ways of doing the motion planner. One that output exactly steering and acceleration and braking, for example, while the other one could be simply a sequence of states that then will have to be transformed into acceleration, braking, and steering. The motion planner output is fed into the vehicle actuation system. Now, why this is not fed into the vehicle itself? Normally, a vehicle built by OEMs, original equipment manufacturer, have already their low-level controller. This is a very well-tuned controller that track certain command. Here I give some example, like the steer-by-wire, electronic throttle, and so on. So this information feeds the vehicle actuation system and eventually go into the vehicle. And this is what we call the vehicle itself. So if you can see here, I've given a little bit of detail of the overall architecture of autonomous driving, but I split this architecture into the three components: the vehicle, the decision making, and the perception. And what's going to happen later on is I'm going to ignore the vehicle itself. This is pretty much the hardware with some low-level controllers, and I'm gonna split the decision-making part and the perception into kind of higher level blocks, and then I'm going to ignore the perception completely, not because it's not important, but because it's not the focus of this lecture, and also focus on the decision-making part. So this is a way of splitting the perception layer into more abstract blocks. Is a way of doing it, and I think it's pretty common. I've seen very often presented in articles and in real-life implementation. So there is one part that's the traffic signalization, there is a part that's the object tracker, then mapper localization and offline maps, they kind of all work together to do simultaneous localization and mapping, and odometry and sensor, these are the more traditional type of sensing. This part of the software stack, the perception layer, interacts very closely to the decision-making part. As you can see here, the reason why I've drawn this arrow is because there is not a cascaded connection between perception and decision-making, but there is a connection at various levels. And for the remainder of this lecture and the following lecture, I'm going to focus only on the decision-making part. And I'm going to split the decision-making part into some sub-blocks, namely the route planner, the path planner, the behavior selector, the motion planner, the obstacle avoider, and the controller. As I've already implied and actually mentioned a few times, this is not the only way of splitting the decision-making part, but is kind of standard. I've seen it used often, and I think it's a good way of compartmentalize the various components. Why do we tend to split the decision-making part into these 6 blocks? Is because there is a progression here on your slide from the left to right on various parts. For example, from the timing domain, on the left we have very slow updates, maybe we're talking about minutes to hours for the route planner, and on the right we have very fast updates, maybe talking about milliseconds for the controller. This is how often new information is fed into the system. And in between, for example, for the path planner, behavior selector, maybe we're talking about minutes to seconds, while for the motion planner and obstacle avoider part, we're talking of hundreds of milliseconds typically. Also, again, starting from the left, we tend to have long look-ahead horizon upstream of the planner. So, for example, the route planner will probably look ahead into kilometers. By the way, the route planner can look ahead for the whole route, whatever that is. While, as we go down the cascade towards the low-level controllers, we have very short look-ahead horizon in terms of meters, or maybe no horizons at all. We tend to have controllers that, like a PID controller, that are purely reactive. And in between the path planner and the behavior selector, maybe we have look ahead horizon of hundreds of meters, while this goes down to tens of meters for the motion planner and the obstacle avoider. Also, starting upstream from the route planner, we have lower safety concern. If the route is not planned correctly, it's annoying, but it's not a big issue. While on the other hand, downstream, as we get closer to the low-level controller, there are high safety concerns. Actuator needs to be controlled in a certain manner. And one final point to mention, to the left, upstream, the algorithms tend to be complex, well, the decision-making tend to be complex, and normally the solution is heuristic. While downstream, the decision-making tend to be simpler. By simple, I mean mathematically easier to deal with, and the algorithm, therefore, tend to be more deterministic. Okay, so this is possibly a reason why the decision-making process has been split into the 6 blocks. And another way of looking into this is that upstream, we have the strategical part of decision-making. This normally includes the route planner and the path planner. In the middle, we have the tactical plan. Okay, now that we have the strategy, how are we going to implement the strategy? And this is the behavior layer, the motion planner layer, and the obstacle avoider. And finally, there is the operational plan. Now we decided on the tactic. These are the commands that will be going to be sent to the actuator to be able to follow the strategy. So this is yet another way of looking into things. I'm aware of companies that actually have internal departments split in this particular way. Yet another way of looking at this is that what comes upstream is the motion strategy. So again, deciding how to move the vehicle. And within the motion strategy, we have what is called the scope for motion planning. So we leave the route planner outside. From the path planner to the obstacle avoider is what some people call the whole thing the motion planner. I give a slightly different definition. I call this the scope for motion planner, while the motion planner itself is one particular block within this area. And within the scope for motion planner, we have the decision-making part, which are the path planner and the behavior selector. What sometimes is called the generation, which is the motion planner. So generation in terms of generating a trajectory for the decision-making part. And then the deformation. This is called deformation because it's something, once we have a trajectory generated by the motion planner, we might want to deform or slightly modify this trajectory in order to avoid an obstacle. I'm going to mention this other partitioning of the decision-making process as a motion planner solved almost as a single problem. And actually I've got a specific lecture based on a particular piece of research which sees the overall problem pretty much solved as a single problem. And if you can see, the gray blocks is in between the path planner and the controller, because this is a little bit of a gray area, exactly how a path planner is defined, and on the other hand, exactly how a controller is defined. So I'm going to talk later on about this particular approach where most of the decision making is solved as a one-shot problem. Okay, so this is the end of this first lecture. What I want you to remember, if you have to forget about everything else, is that the decision-making part of motion planner is pretty much a cascaded approach. And there is a reason why it's cascaded, because upstream we have decisions that are slow to make and not very safety critical, and maybe with a very long horizon, while downstream we have very fast decision to make with very short horizon, maybe no horizon at all, which are also very safety critical. And also I want to make a point that is still very unclear where some of this boundary is. This is a good general framework, but there are no standards yet, and various companies or various research group might split the decision-making part into different blocks. So this is the end of the first lecture. I'm looking forward to see you again in lecture 2. Hello again. This is the second of a series of videos developed for the Autoware Foundation, and in particular for the Autoware Academy. In this second short video, I will be unpacking a little bit more the details of the various blocks that form the decision-making process in autonomous driving. So we saw in the previous lecture the general framework. We split this framework into 6 blocks. Each block serves a purpose, performs a function. Here we're going to see what kind of algorithms run within these blocks and what the input and output of these blocks are. If you think that at the end of this video you will have enough information to go off and write your own decision-making code for autonomous driving, I think that's a little bit optimistic. What I think the purpose of this video is that if you don't know anything at all about decision-making in autonomous driving, you will have a good overview and pointers to the right direction where to start to look for. If you already are an expert, maybe in some specific areas of decision-making, you will see where your expertise fits within the general picture. I've chosen a framework that I think is the one that is kind of widely accepted, both in academia and industry, and also a framework that allows me to depict and describe some algorithms that make autonomous driving possible. Okay, so this is where we left it last time. We have identified the 6 blocks making up the decision-making part of autonomous driving. We're going to see what's inside each of the 6 blocks. And by the way, I've used this particular paper to define the structure. I think it's quite comprehensive, and I recommend anyone interested in autonomous driving for the decision part of autonomous driving to have a look at the details. So let's start from the route planner. So the route planner is the block responsible for computing a route. Effectively, this works like a sat-nav system. This block, the output of this block, is a sequence of waypoints in x and y coordinates. So of course, like a sat-nav system, you know where the starting position is. You give a coordinates of an ending position, and the route planner will figure out which waypoints you have to go through to be able to go through that position. And for a road, so for a structured space like a road network, this is defined as a graph. I'm not going to explain the details of what a graph is, but you probably remember that it's a set of vertices and edges. And in this case, a vertex corresponds to an x and y position, and an edge is a connection between these between two vertices, and also an edge contains information about the cost of moving from one vertex or one node to another. So vertices for route planners are waypoints, and edge are costs for traveling along the segment. So these are the methods that are commonly used for route planning. Let's start from the goal-directed method. This is a search from the source to a target vertex. A-star is a classic algorithm for this. We will see A-star algorithm appearing more than once throughout these classes. The separated-based method is yet another way to perform the route planner. So in this method, we kind of coarsify the graph by a vertex separator. So this is to superimpose another graph that is a simplified version of the underlying graph. Of course, the reason for that is for reducing computational complexity. So a vertex separator is a small subset of vertices, so a smaller graph. And this creates an overlay graph, which is much smaller, and therefore is faster for a search algorithm to find a route from a beginning to an end. Another method is the hierarchical methods. This exploits the hierarchy of road networks. To give an example, to go from A to B, there might be a lot of countryside lanes, but also a motorway. So with this method, we will start from the motorway, if motorway is an allowed path. That, of course, we will simplify the graph, but we will simplify the graph starting from some knowledge about the different vertices and edges that make up of this graph, because we're talking about roadway network. If this method is particularly useful if you're trying to connect two very far away points, it makes sense to consider large network, large roads first, and then go into smaller road. Finally, there's this other method called the bounded hop method. Here we add virtual shortcuts, so we make up a connection between two vertices that doesn't exist, but this connection possibly is the shortest distance, and we pre-compute the distances between these vertices. And sorry for skipping to the next one. So with this method, we make yet another approximation, which is based on the fact that we know pretty much what the shortest direction is, and then we're trying to fit a path to go there that is constrained by the actual route. So this is enough for the route planner. The output of the route planner, which is a sequence of waypoints, will be fed into the path planner. So the path planner computes path for a given route. A path is a sequence of poses, and a pose is an x and y position plus an orientation. So this is an important point to make, that a pose is not, we're not just interested in the x-y position of a vehicle, we're also interested in this orientation. And this is possibly because vehicles are so-called non-holomonic systems. I'm not going to say much about non-holomicity, but this is to do with the fact that there are non-integrable constraints. But in any case, a path planner, it kind of refine the path given by the route planner and trying to find actually more realistic way of moving from point A to point B. These are the two most common methods used. The graph search method, trying to find the best path between current goal and state goal. It's also a search space discretized method, so the search space is discretized somehow. And then a graph is imposed on top of the search space on an occupancy grid map. Dijkstra or D-star algorithm are also common method for the graph search method. So again, I haven't said much about Dijkstra or A-star, but have a look at this method. It's super important for path planning. A-star is it builds on top of Dijkstra, which is more... Dijkstra you can see as a search method, which is like a wave, trying to figure out all the possible way to get from A to B, and then calculate the shortest possible path. A-star uses some heuristics to find the shortest path, so it's quicker, it's more prone to mistake, but in practice it works much better. Curve interpolation is another widely used method for path planners. Here we're trying to find a set of points by interpolating between two waypoints. Splines are often used, so it could be spline or it could be any other method for fitting curves through points. The result, of course, is not optimal. It's difficult to guarantee constraints, vehicular constraints. For example, is the vehicle able to do this turn at this particular speed? But normally these curves are smooth enough for these methods to work in practice. So the path planner will give a more refined path that then will be fed into the behavior selector. And the behavior selector is an interesting one. Here is where decision is made about the actual behavior of the driving. For example, a number of paths might be fed into the behavior selector, and now the behavior selector is picking up the one that it prefers according to some matrix or according to some criteria. For example, the behavior might select to keep lane keeping, so there is a path for lane keeping and the behavior selector is sticking to that. There is now a moment where you might want to go through an intersection, and the behavior selector is selecting the behavior through the intersection, selecting the behavior through traffic light, and so on. And all of that is done exactly by selecting one of the paths outputted by the previous block. So the behavior selector is often considered the ethical element. Say, the typical trolley example, if I have to make a decision whether to carry on my normal route and kill a lot of people or turn and kill one people instead, what should I do? And this has attracted a lot of attention and a lot of discussion, especially over a beer, on what autonomous vehicles should do. My personal opinion is that this is not an engineering problem. We shouldn't worry about this for two reasons. One, because how often does that actually happen that you have to make some decisions? Two, if we knew as human what the right choice would be, then that's easy to program. This is not an engineering program, it's more a philosophical, ethical type of problem. But the behavior selector is indeed considered the ethical element in autonomous driving. And this block usually uses a combination of heuristic and finite state machines to select the right behavior. Methods are indeed the finite state machines, so discretized rule based on traffic, and it's often actually difficult to model because uncertain in very complex scenarios. So the finite states work very well in simple scenario. Imagine like a motorway driving, where possibly the only choice you have is either keeping on the lane or change lane. But imagine a very complex urban intersection, and you can see how the finite state machine becomes very complex very quickly. Then there is this other set of methods called ontology-based. Ontology is sort of some sort of knowledge-based method. So ontology is a framework for knowledge representation. It considers rules of the road and makes decisions such as I'm going to stop, I'm going to go right, left, and so on. And it kind of builds a complex model at each location, and this complex model actually needs to be built manually. So also this method tends to become quite cumbersome in a complex scenario. And finally, there is a large class of methods broadly summarized as Markov decision processes. These are actually widely used. They can handle uncertainty in action transition. If you know what a Markov decision process is, you will see that's quite the case. So you define two particular scenarios, and in between is some sort of probabilistic distribution of cases. Can also handle uncertainty in perception. That's an interesting thing, because although we're discussing about decision making, you will still have to deal with uncertainty in perception, and this method normally can be robust against error coming from the perception layer. And the assumption is that other vehicle will also follow the rules, or will also follow this probabilistic transition in the Markovian decision matrix. So the information for the behavior selector now are finally fed to the what people normally call the motion planner. So the motion planner computes a trajectory from the current state to the current goal. And by the way, a goal is not necessarily an XY coordinate. A goal could be, for example, making progress along a road. The trajectory follows the path selected by the behavior selector. So in a way, you could see the motion planner as an algorithm that makes a smooth trajectory based on the trajectory output of the behavior selector, and also the trajectory, the motion planner, hopefully, is a physical trajectory. So it's a trajectory that takes into account the physical constraints of the vehicle. So the trajectory needs to satisfy the kinematic and dynamics constraints. For example, tire limits or acceleration constraints of a vehicle. It might satisfy other constraints. For example, the maximum rate of turn is you're being realistic to calculate a trajectory with a rate of turn, for example, that is beyond what the physical actuator can provide. And the motion planner should take into account these physical constraints. It also takes into account safety. For example, keeping stability of the vehicle. It can also consider kind of higher level requirements, for example, comfort, minimizing some acceleration that can make the passengers feel uncomfortable, or eco-driving, which is to say, driving in a way that minimizes the energy consumed. So, by the way, a trajectory can be defined in two ways. As a sequence of actuators command. So a sequence of actuators command is literally turn the wheel by so many degrees, or accelerate by so much, or apply a braking force of so much. So this command can be actually sent directly into your actuators if the update rate is high enough, or motion planner can simply output a sequence of states. And in that case, you will definitely need a low-level controller that then maps these states into actuators command. It's important to distinguish between two types of driving here. Structured space driving, for example, road with lane, with unstructured space driving, for example, driving an open area. like a car park. The distinction is important because in structured space you can make some assumption. For example, that you're driving along a lane and your objective is to make progress along the path. While in structured space, the problem is slightly different. Now you want to drive the vehicle from location A to location B. And by the way, I'm wrong to say location. I should say pose A to pose B, because the orientation of the vehicle also matters. And here the type of algorithm we use is slightly different. And it's a slightly different problem to solve anyway. So the method used for motion planner are again graph search. This is an extension of technique used for motion planner. So the same graph search methods that we described for motion planner can be used here, but more refined, maybe including more states. Common use methods are the state lattice method, elastic band, and A-star again. I will say more on the next lecture, by the way, regarding these methods. The sampling-based method is another one. Here we kind of randomly sample, we create random sample of the state space, and then we're trying to look at trajectory along this random sample. The commonly used method is the so-called rapid exploring random tree. It seems counterintuitive that actually using random point is a good idea, but in fact, in practice, these random methods, for example, the RTT method, provide very quick solutions that can then be verified later on to make sure that actually the solution is feasible and applicable. There are also curve interpolation methods. These are similar to what I described earlier. These are methods that are trying to find smooth trajectory to interpolate points. Clothoid curve are commonly used because in clothoid curve you have a smooth transition, for example, between a straight line and a curved line. And actually the interesting thing is that roads are built using clothoid curves. So by using this method, you automatically take into account the inherent structure of the way roads have been designed. Finally, there is another class of method called numerical optimization method. This is my favorite. In this method, we actually solve an optimization problem for given objective and constraints. So we transform the motion planning problem into an optimization problem. The skill here is not so much to solve the problem. There are a lot of good solvers out there. The skill here is to convert the motion planning problem into an optimization problem with the right objective function and the right constraints. Nonlinear model predictive control is commonly used. You will see more later on. In this method, it's very easy to consider dynamics of the vehicle and various constraints. The drawback that is normally cited for numerical optimization is the high computational cost. But having said that, if the problem is set up in the right way and the right algorithm are used to solve the problem, actually numerical optimization works and can be implemented in real time. So, moving downstream from the motion planner, now the trajectory that's been generated from the motion planner is fed into something called the obstacle avoider. The obstacle avoider is an algorithm that actually tweaks the trajectory to avoid collisions. So in case something pops up last minute, the obstacle avoider is responsible to trying to figure out if there is another way of avoiding the obstacle. Often the obstacle avoider is a very simple algorithm that slams on the brake and tries to reduce the speed to avoid a collision. The obstacle avoider can actually use information directly coming from the perception layer to assess risk. So the idea of the obstacle avoider is to provide this very fast loop to have yet a final chance to avoid a collision if something changes very quickly. Something pops up in front of the vehicle, rather than having to recalculate the motion planning and recalculate new trajectory, with the obstacle avoider, we can tweak that trajectory to avoid the collision. This, of course, is a safety critical component, as you might have gathered. So normally the obstacle avoider is as simple as possible. The simpler, the better. And finally, the trajectory that might or maybe not be tweaked by the obstacle avoider is fed into a controller. This is sometimes called the low-level controller or the tracker. So the controller uses the trajectory as a set point and calculates and sends commands to the actuator. And this command, of course, are steering, accelerating, and braking in a standard vehicle. A controller can simply be a PID loop. You might remember from your control classes that PID stands for proportional integral derivative. So this is a very simple reactive controller that tracks a particular set point, but also nonlinear multiplicative control here could be used. Method we can distinguish the method into two. One, direct actuation. So here, if we assume that the trajectory is already a sequence of command, we could actually send the trajectory right down to the actuator, or we can simply provide another fast loop, a control loop to track the command. If the trajectory, on the other hand, is a sequence of state, then this other set of methods called path tracking will transform the state into actuator command. So the path tracking method will provide fast feedback control loop to track states. The pure pursuit algorithm is a common and simple method. If you never heard of the pure pursuit, I recommend to have a quick look, because it is such a classic that I think anyone who says taking a course into motion planner should know. But MPC is a much more performing method, and as I kind of implied earlier, these days there are very fast solvers for this type of problem that real timeness is not so much of an issue. Okay, so this is all I want to say about the second lecture. Takeaway point for the short videos are decision making in autonomous driving is indeed a cascade of functions. I've described here 6 functions, but it could be less or it could be more, depending on how you architect your system. Boundary between each function are quite arbitrary. Later on you will see another example where boundaries are defined in a slightly different way. And the algorithm choice is a compromise between computational speed, so trying to react to disturbances, to new situations as quickly as possible, but at the same time trying to generate an accurate plan for your vehicle. And of course, choice is highly dependent on the safety level required. You can have a very simple implementation that is not very safe. On the other hand, what we hope to achieve is a very safe implementation, which will require some careful choice of algorithms to be able to be safe, accurate, and computationally fast enough. Okay, on the next lecture, I'm gonna take out the route plan, not because it's not important, but because it's a big topic on its own. I'm gonna take out the controller, again, not because it's not important, but it's another big topic on its own, and I'm gonna focus to those 4 blocks that define what people often call the scope for motion planning. Hello again, everyone. This is the third of a series of short video delivered and prepared for the Autoware Academy. In this video, I'm gonna focus more on the problem of motion planning. And in particular, I'm going to show you, there are so many algorithms used in the motion planning problem. I'm going to show you a way to categorize this algorithm into 3 big subdomains based on the type of output these algorithms have, the space-time properties of these algorithms, and also the kind of mathematical domain they belong to. So it's going to be a kind of, again, another overview video to see how everything fits together for the particular problem of motion planning. But I'm going to take the opportunity of this introduction to say a word of warning from my side about motion planning in general. Motion planning for autonomous driving is being driven mainly by people coming from a robotic background. And the robotic community has been developing stuff for motion planning way before autonomous driving was taken seriously by anyone, and they've done an excellent job. But robotic people tend to have some sort of kinematic approach. They tend to somehow ignore dynamics or consider vehicle dynamics as a post effect. and deal with them later on. On the other hand, there is a big community of vehicle dynamics who understands vehicle dynamics extremely well. And when I say vehicle dynamics, we're talking here about, for example, a tire-road interaction, or the position of the center of gravity of a vehicle, and so on. So vehicle dynamicists understand vehicle dynamics very well, but not so much motion planning. I think what is extremely important these days to do motion planning for road vehicles is for the two community to join up effort, which is happening anyway. But the reason why I'm mentioning this word of warning now is to make sure we understand that a lot of its algorithms are very kinematics, are okay for a certain type of motion planning, but where things become complicated, for example, in very low friction surfaces, standard algorithms might not be the perfect choice. But let's see what this classification is all about. Okay, so we've seen these particular 4 blocks, the path planner, behavior selector, motion planner, and obstacle avoider, as the blocks that define the scope for motion planning. So this is where the motion planning is happening. And among the various definitions are found for motion planning, this is the one I like the most. So the motion planner decides the most convenient motion strategy for some chosen criteria. And there are a lot of important points here to consider. First of all, decides what the sides mean, what most convenient mean, and what the chosen criteria are. These actually are very fundamental problem in motion planning. But let me tell you the way I see these, what these chosen criteria are and what most convenient mean. We can define some sort of a hierarchy of criteria. You know, we need to drive a vehicle from A to B, or we need to have this vehicle follow a particular trajectory or make progress within a road. What are the things that we need to consider? So first of all, I'm going to put point number 0 is the law of physics. And it sounds very obvious, but a lot of badly designed motion planner kind of ignore the law of physics, send a trajectory, a motion planning command to the actuators, and then they hope that the low-level controllers or whatever you have there can take into account the law of physics. So this is not something, the law of physics, you can't escape, it's out there, but the more you take this into account at your planning stage, the less you leave it to chance in the real world. So that has to put as a number 0. Then number 1 in terms of consideration is, of course, safety. I don't think anyone has in mind to design a motion planner that doesn't consider safe at the very bottom level of decision making. And of course, by safety here, I'm thinking about not hitting any obstacles or not hurting anyone. Above safety, I would say there is legality. Once your motion planner can satisfy the safety requirement, the second thing you should care about is that you're respecting the rules of the road. On top of legality, I like to think that the next constraint or requirement is physical and mental comfort. And what I mean by that is physical comfort in things like motion sickness, or actually feeling comfortable within a vehicle being driven by a robot. And what I mean by mental comfort is what some people also call a perceived safety. And remember that an autonomously driven vehicle could be perfectly safe, but if it doesn't feel safe, that could give you some mental discomfort. And at the top of this pyramid, I will put other considerations such as energy time efficiency. So once safety, legality, and comfort is being accounted for, then the motion planner could do things such as optimizing journey times or optimizing or minimizing energy constraints. Okay, so let's go into the core of this lecture, which is how to classify various algorithms. And I've used this particular publication here, which is freely available. So I borrowed the classification from what the authors have done in here. So I suggest you have a look at the publication itself if you'd like to have more details. So the algorithms could be classified into 3 big domains depending on the type of output. For example, is the output a space? Is it a path? Is it a particular trajectory, a trajectory of waypoints or a trajectory of states? Is it a maneuver, so some sort of high-level information such as overtake or keep the lane, or is even a symbolic representation? So this is one classification that can be made based on their type of output. Another classification that can be made is based on their space-time property of the algorithms. And this is basically to say, is the algorithms as some sort of predictive or reactive nature. So if you're familiar, for example, with dynamic programming or model predictive control, you already know that these are predictive type of algorithms, while reactive algorithms could be very simple control loops like a PID controller. And finally, the third classification is to do with the mathematical domain the algorithms belong to. So this is the philosophy of the approach and the framework of the solver of what the algorithm is trying to figure out. So let's have a look at now a sub-classification of the algorithm. So within the type of output algorithm, we can define so-called set algorithms. This algorithm returns only at the composition rather than a reference. So the positive of such algorithm is that they provide a more natural representation of the motion planner. The cons are that a complementary algorithm, so another algorithm is needed to be able to convert the composition into something that is more useful. Then there is another class of algorithm called solve algorithms. This algorithm can directly generate a trajectory. So the pros are that the trajectory is readily available. The cons are this algorithm could be a little bit less intuitive in the way they are constructed. So a little bit more knowledge is required to set them up and required to set them up in a way that the solution you get is useful and most of all correct. Among the space-time properties, we have we can consider algorithms with a predictive horizon. So these algorithms that are able to plan ahead. This algorithm, if you remember the cascade of the 6 blocks we've seen earlier, these algorithms tend to be more to the left, more upstreams. So the pros, of course, is that they have better performance. No doubt, if you can have some sort of prediction of what's going to happen in the future, if you have a big look ahead, you can perform better. The cons, of course, is that they could be very computationally demanding. Think about dynamic programming type of algorithms. They can, they explode in complexity as dimensions increase. Reactive algorithms, this is a kind of traditional feedback control algorithm, so the process are very simple to implement. In fact, these algorithms are implemented to the right, so downstream of the cascade of functions for motion planning, and the cons are only suitable for tracking. So these are very good algorithms to do very simple things and also very suitable for safety critical applications where complexity is not necessarily a good thing. And on the third big classification in terms of mathematical domain, we can distinguish algorithms in terms of geometrics. So they make use of the property of space. The pros of this algorithm is that they can work directly with space constraints. The cons is that it will become difficult to deal with large space explorations. Heuristic types of algorithms depend specifically on the knowledge you have on the problem. Of course, if you don't have any knowledge, it's difficult to use these algorithms. The pros is that they can solve problems more quickly. There are no guarantees, of course, these are heuristics, but you gain in speed. So yes, the lack of theoretical guarantees are the main drawback of heuristic algorithms. Then there is the big class of logic algorithms. These are deductive approaches built on assertion. So the pros are you can easily see the link between cause and effect, and the cons are there could be a combinatorial explosion. If the number of logical operations is large, including all the possible interaction, this will become very difficult to write down and implement. Then we have another class of algorithm that can be put under the umbrella of cognitive algorithms. These are evaluation based on situations and based on previous knowledge. The pros is, of course, their ability of using this existing knowledge and gather new information, so these algorithms are able to learn. The difficulty with cognitive approach is that they are difficult to validate. Someone once told me that the problem of a decision-making process that resemble more and more the human cognitive approach is that they will end up making the same errors that humans make. And if the aim is to have a decision-making process that are almost error-free, then dealing with cognitive type of algorithm is going to be a challenge. And finally, there is another class of what we can call the biomimetic algorithms. So these are some sort of a physics-inspired approach. The process are very intuitive, very easy to understand, very simple to implement, but the drawbacks is that can be suboptimal. It can, of course, generate unexpected behavior if the situation becomes more complex. So I want to give this classification because I find it very useful to sort of put into boxes all the algorithms that are out there. I haven't said a single word about specific algorithms, but I'm just giving this structure. So maybe in the future, if you hear about an algorithm that it hasn't been mentioned in this lecture, you can try to play around to see if you can put it in the right box. So the takeaway point from here is that there is an hierarchy of decision making, and there is a way to classify these algorithms into 9 domains. This is not the only way, but it's a way I think is indeed useful to be able to understand further. On the next lecture, we're going to see and going to discuss specific algorithms based on their classification, and in particular, going to discuss so-called space configuration algorithms, pathfinding algorithms, algorithms that can be classified under attractive and repulsive forces, parametric and semi-parametric curve-based algorithms, artificial intelligence, which is a huge topic, of course. I'm just going to say a few things. And finally, my favorite, which is algorithm based on numerical optimization. Hello again, and welcome to the fourth of the series of lectures prepared and delivered for the Autoware Academy. In the previous lecture, I presented a taxonomy to give some structure on how various algorithms that have made motion planning possible could be analyzed and categorized. What I'm going to do in this lecture is to actually classify the algorithms into 6 big areas according to their properties. And if the previous lecture felt a little bit abstract, a little bit unclear why that particular taxonomy was chosen, maybe after this lecture things will become clearer, and maybe you can go back to the previous lecture and see if you can find mapping between algorithms and their classifications. So I won't be diving into the details of motion planning algorithms. I only going to mention what they are and how they work. If you are already an expert in motion planning, hopefully this lecture will give you a nice overview of how everything fits together. If you kind of new in the area, again, you won't be able to program your own motion planning algorithm, but you will be able to go online or find a book and search for how these algorithms actually work. Right, okay, so let's have a look at this classification of motion planning algorithms into these 6 classes, which are the space configuration type of algorithms, pathfinding algorithms, attractive and repulsive forces algorithms, parametric and semi-parametric curves, artificial intelligence, and last but not least, my favorite, the numerical optimization class of algorithms. This classification, by the way, follows this recent work, so I recommend anyone interested in this area to go and have a look at the original publication. So let's start from the space configuration class of algorithms. These are geometric methods. The challenge in the geometric methods is to find the right space configuration parameters. These algorithms could be sample-based, The sample-based algorithm works basically by having samples of the space in front of the ego vehicle, the car. One of the sample will be the goal state. Other sample might coincide with some obstacle. And then, of course, the aim of the algorithm is to find a sequence of sample that is a feasible sequence in a sense that will return a drivable path. Another way to divide the space, and by the way, as you notice, the space configuration algorithms are effectively way of dividing a two-dimensional space. So the other way is the so-called connect cell. So you divide the space here into areas. So rather than point, this is particular areas. And similar as we've seen for the sample-based algorithms, here there will be some areas where the vehicle is allowed to go, some areas which correspond to an obstacle, and the aim of the algorithm is to find a path among a drivable space, a feasible area. And finally, there is another class of algorithms called lattice algorithms. The way this works is a little bit different. So each space is divided in blocks, and each block has a regular structure with some motion primitives. In this particular example, it's 5 motion primitives. And these are kind of predefined and feasible maneuvers. And every time you move from a cell to another, the aim of the algorithm is to choose which one of these primitive maneuvers should be implemented. And again, as you can see here, some maneuvers like the one depicted in red are not possible. Other maneuvers like the one depicted in blue are possible, but they're not really helping towards our goal state. And a functioning algorithm will come up with choosing what is depicted here as the green arrows, which is the path to reach a goal state. So these are the 3 main way of dividing the drivable space and the algorithms that make up the space configuration class. Let's move now to another type of algorithms called the pathfinding algorithms. Here the aim is to find a path in a graph in order to optimize a cost function. And if you remember, if you follow the previous lecture, we've seen these algorithms before. We already say something about it. So they're mainly used for route planning and local planning. Let's see what these algorithms are. They're all kind of based on the Dijkstra algorithm or A-star. And as you can see here, we have a sequence of points or waypoints, which can represent edges or nodes in a graph. And the task of the algorithm is to find effectively the shortest path according to some measure, not necessarily a distance measure, along this path. If you don't know the difference, A-star is pretty much like the Dijkstra. The only difference that A-star tries to look for a better path using some heuristic function that makes it much faster, but of course is also an approximation. Another important class of pathfinding algorithm is the so-called rapidly exploring random tree. These algorithms are specifically suitable for finding effective solutions in non-convex and highly dimensional spaces. So this tree is constructed incrementally by finding these random points according to some criteria. Such class of algorithm can easily handle problems with obstacle and differential constraints like non-holomonic constraints. A vehicle is a system with non-holomonic constraints. RT algorithm can also be considered some Monte Carlo methods to bias a search into the largest Voronoi region of a graph in a configuration space. The third class of algorithm I want to present are so-called attractive and repulsive forces. So this algorithm kind of use some intuitive understanding of a vehicle can move along a path by being attracted or repulsed in a certain way. So the evolution space is defined as attractive forces for desired motion and as repulsive forces for undesirable motion. And the motion of the vehicle is guided by the resultant force vector. So there is no space decomposition here. It's pretty much a vector field where the ego vehicle will move through. And in fact, they work well, and they work actually particularly well with continuous spaces. So I'm going to show two of these algorithms. One is the so-called artificial potential field. Here in this method, we assume that the vehicle moves in an abstract artificial force field. As you can see here, there is an attraction force and repulsive force given by obstacles. Another type of algorithm is so-called elastic band models. These are mainly used for lateral control and for obstacle avoidance. So the environment is modeled as a spring mass system. So if you think a car moving through a field with obstacles and trying to maximize the distance between these obstacles, maybe a distance also proportional by the relative speed between obstacles, then having stiffness in springs that somehow reflect how far you want to be from this obstacle will give you a solution that goes through obstacles. The fourth class of algorithm is the parametric and semi-parametric curves. These are geometric methods. They are particularly suitable for highway driving, so for a structured space where we have lanes. These are curve-based algorithms, and that can implicitly take into account the kinematic constraints of the vehicle. I'm going to describe two here. One is the point-free algorithm, for example, tentacle schemes. So this, the point-free method builds kinematically a feasible trajectory as a set of candidate solutions, which are basically maneuver. As you build up this maneuver, then you need another algorithm, another decision maker to choose the most convenient among these maneuver. The other set of methods are called point-based methods, and these are methods that use curves to fit waypoints, which could be sampling points or cells. So the output is a path of a trajectory. The line of curves can be used to have properties such as minimum length or minimum curvature, so they can include curvature constraints. Clothoid functions, as we've seen earlier, are good for smoothness. And the important thing, the reason is that roads are built on clothoids. Roads are basically either straight line or clothoid curves. For lane changing, like in this particular example, sigmoid functions are typically used. So spline curves have good properties, and Bezier, like the curve showed here, which are a type of spline, effectively are an important class of spline. The important thing, remember, with Bezier curves is that you don't necessarily go through waypoints, so you can do cut through some corners. So these algorithms have to be used with care. Now, the fifth class of motion planning algorithm can be all grouped under the umbrella of artificial intelligence. And there is so much there that I'm not going to even try to explain and classify everything that can be described after artificial intelligence, but just give some general guidelines. So what artificial intelligence algorithms effectively do, they try to simulate human reasoning and learning. For that, they are generic and flexible, which is both an advantage and a disadvantage. An advantage is because they can learn, so automatically they can end up doing the right thing. The disadvantage is that you lose determinism. You don't know exactly what they learned and how they learned, and then of course could be disastrous in motion planning. So they're mostly used actually for predictive planning, which is less safety critical than, remember, predictive planning comes more upstream, is more on the left on the sequence of block diagrams that we saw earlier. So the way we can classify artificial intelligence algorithms are the human-like type of algorithm. These are risk estimator, taxonomy models of game theoretical type of models. Then we have heuristic type of algorithms. These are support vector machine and evolutionary methods. Then we have the so-called approximate reasoning algorithms like fuzzy logic, artificial neural network, and reinforcement learning. And finally, the logic-based type of algorithm, which are more rigid, of course, difficult to implement when the logic can become difficult. These are rule-based algorithms, decision trees, and finite state machines. The final class for motion planning algorithms are numerical optimization methods. So in numerical optimization, they work in a completely different way. Here we effectively trying to minimize a cost function. So the majority of skills come into setting up the problem correctly, so setting up the cost function correctly, and then setting up the constraints and everything else that needs to be defined to solve the problem. These are well-defined mathematical models. They tend to be more deterministic, meaning that despite their potential complexity, the output should be more repeatable and reliable. They can easily handle constraints. It's an optimization problem. You optimize to solve given certain constraints, so they can handle that automatically. And model predictive control is a highly popular method. So model predictive control use numerical optimization to find a solution to the motion planning control problem. The solution often require the solution of a nonlinear programming problems. Such problem, if not set up correctly, they could be difficult to solve, but these days there are good solvers for finding effective solution in real time. The problem is nonlinear because vehicle dynamics are inherently nonlinear. Some approximation have been proposed out there where you first linearize the nonlinear model of the vehicle around some operating point, so you can actually solve a linear problem or a quadratic problem effectively at each linearization point, but this is a matter of trade-off to see whether the approximation you want to use is suitable. But in general, if you're controlling a vehicle, the vehicle is a nonlinear system, and therefore a nonlinear programming problem will have to be solved. Dynamic programming is another method widely used for, especially for finding global solutions. There is the curse of dimensionality with dynamic programming, but on the other hand, you can easily deal with nonlinearities. And let's have a look at what an optimization problem looks like. This is a generic form. If you've never seen things like that before, don't get scared by the notation. We'll try to explain what the things mean. So at the beginning, most of all, we need to have an objective function. Objective function is effectively a mathematical description of the goal that you're trying to achieve. The goal could be hitting a goal state, or it could be, for example, making progress along a path. Then you need to have, of course, some constraints. These are linear or, equality or inequality constraint. One of the constraints is the measurement or the estimate of the vehicle state. Equality constraints, are the system dynamics, so effectively how a vehicle functions. There might be some final equality constraint. For example, you want the vehicle to be at a particular state at the end of your optimization. There are up and lower bounds. These are inequality constraints, for example, actuator limits or space limits. And then you can also include integer variables to make the problem more complex, and you can also include nonlinear constraints. So this is pretty much the form of a numerical optimization problem. If you can describe your motion planning problem into this problem, then you are ready-made solvers for finding a solution to that. So the takeaway point of this lecture is that I present a classification of algorithms for motion planning. The focus here was more on structure environment, I have to say. So these algorithms are particularly suitable for highway driving. From a structure space, things can be a little bit more complicated. And I hope this lecture kind of helped you to make sense of the huge literature in this area. In the paper I'm referring to, they have very interesting spider maps where you can see now how the algorithms map to the taxonomy we discussed in the previous lecture. Say, for example, for space configuration algorithm, we can see that these are geometric methods and set algorithms in particular. For optimization algorithm, the last one I've described in this talk, these are solve algorithm and predictive horizon algorithm, but also highly use of logic and heuristic. And again, if you refer to the paper, I'm not gonna say much here, you can see the mapping between algorithms type and taxonomy made for all the other algorithms we have discussed. Okay, so this concludes lecture 4. It also concludes the this architecture I presented. So we started, if you remember, from lecture 1, looking at the full architecture of autonomous driving. Then we focused on the decision-making part. Then we went down to another layer of motion planning, and that's where we stopped. What's going to happen next? I'm going to deliver another 2 lectures, one on a particular control technique called model predictive control, and another one on a more advanced method for motion planning. Hello again, and welcome to the 5th of this series of lectures developed for the Autoware Academy. In this lecture, I'm going to talk about MPC, Model Predictive Control, and there is so much out there that, trying to cover MPC in a few minutes will be an impossible task. And there is so much as well to know about mathematical optimization even before starting understanding MPC. What I decided to do this time, which I think is slightly different to what you can already find on the web or a standard university lecture, is to try to answer some questions about model predictive control, which are the questions that I often get asked. So see this talk as a way of either answering questions that you already have or as an input to go and find out more. Model predictive control, frequently asked questions. So here we are again with the 6 blocks that we've been discussing so much in the previous talks. Model predictive control has a scope in the last 3 of these blocks. So I would say from the motion planning all the way down to the lower level control. I don't think actually, you will see in the next lecture that MPC is also used a little bit upstream, but in a very advanced and sophisticated way. So we can assume for now that MPC is more a low-level motion planner type of algorithms all the way down to the low-level control. So that's the scope for MPC. What is MPC? It's an advanced feedback control technique, but let's start from the beginning. What is control? Control is the act to act on a system to make it behave in a desired manner. So if we have no uncertainty, so if you know the reality completely, if you have the perfect model, all we need is this. We have a system, we want to achieve a specific system behavior. All we have to do is to give the computed control action that applied to the system will give us the system behavior. In reality, there are almost always uncertainty. Not always. There are some cases where you can assume that there are no uncertainties, but in most of the control of physical systems, there are uncertainties, so such open loop control technique wouldn't work. So what is feedback control? Is the only way to deal with uncertainty. And this sounds obvious, but I think it's something that people often miss. If there is no uncertainty, there is no need for feedback control. If there is uncertainty, the only way to deal with the uncertainty is by feedback. So in feedback, what we do, we measure, actuate, control, calculate, and act. So again, starting from our system, there is a system behavior that we're trying to achieve. We take some measurement, we put this measurement into a controller, the algorithm, and we calculate the control action. So the controller is actually where we execute our control algorithms. So the simplest control algorithm is a proportion of an error between where we want the system to be and where it actually is. So for this very simple example, a very simple control U is the proportion of a difference between the input R and our measurements X. The control algorithms that compute the sum of the proportion, the integral, and the derivative of the error, guess what it is? That's the PID controller, very famous. If you don't know, if you never heard of the PID controller, have a look at that. Still widely used, PID controllers are super simple to implement. They look at the present, the past, and the future. Sometimes in feedback control, it's more important to have a fast loop than a precise loop. That's where PID controllers still have their place, despite their simplicity. But what if we have more than one input and more than one output? So what if the system diagram looks a little bit more like this? With PID controller, now things become a little bit more complicated. For example, in this case, we have 3 input and 3 output. You have to, you need effectively 9 PID controller to control every possible combination on input and output. 9 times 3, which is the number of parameters you have to tune. The number of parameters becomes very large and unmanageable. And what about we want to control the system optimally? Optimally, for example, is to find the best trade-off between the effort, the energy required to actuate on the system, and actually the ability of reject disturbances, the ability of achieving the desired behavior. You can't simply do that by manually tuning a PID controller unless you do it in a sort of a trial and error fashion. So, what is optimal control? That's the next question. This is a control technique that tries to achieve the best possible result. And what is the best possible result? In mathematical optimization, the best possible results means finding the minimum of a mathematical function, often called the objective function. For instance, something that looks like this. And again, if you've never seen this before, I'll try to explain in simpler terms what this is. This term is a measure of how much the system deviates from the desired behavior. This one is another term that says what is the effort required. And this is a summation from now until the end of time. So basically what we're saying here is that we measure how much we deviate from where we want to be, how much the effort is required. We're going to sum this for every possible step into infinity, and we're trying to minimize that. We're trying to make this the value as small as possible. I've included another term here for completeness. Don't worry about that. This is more of a something that might be useful to have a relationship between the state of the system, the outputs and the inputs, but it's not always necessary. So what is LQR? LQR, or linear quadratic regulator, is a control technique that achieves the best possible result for a quadratic objective. That's what we see in the previous slide. That was a quadratic objective function for a system with linear dynamics. What is LQG? You might have heard of LQG as well, all the 3 letters acronyms that we have. An LQG controller is a controller where some of the system behaviors, or some of the states of the control system, are estimated by a Kalman filter. So you can't always assume that you measure everything you need. Sometimes you need to estimate some of the state of the system by inferring from the measurement you have. If you do that, and if you use a Kalman filter to do that, and you control your system with an LQR controller, that's an LQG controller. So what about constraints? Often we need to make sure that the system behavior and the control actions stay within certain limits. For example, there is a maximum force an actuator can deliver, or a maximum overshoot that we can tolerate. We call such limits constraints. Now we can go back, we got all the ingredients to go back to the original question, which is what is MPC? In its simplest form, an MPC controller is an implementation of an LQR controller, or LQG, if you need to do some estimation. So it's an LQR controller that is also able to satisfy constraints. Again, that's in its very, in its most vanilla of the implementations. This is linear MPC. In constraints, linear MPC and constraint LQR are similar. I'm going to show the constraint LQR problem, and then MPC is actually the implementation of the constraint LQR problem as a feedback control loop. So in the constraint LQR problem, remember this is an optimal control problem, so there is a cost function that we want to minimize, and this is here, and then another set of equations down there, which I'm going to describe in a second. So this is the cost function. We saw actually that earlier. There is an extra term here, Again, this cost function can be built in many different ways. So just accept for the moment, if you never said this before, that this is a mathematical expression of something that we're trying to make as small as possible by selecting U appropriately. This is a measure or estimate of the system states. Remember that MPC effectively is a feedback control policy. So we need measurements of the system states or estimates. These are the so-called equality constraints. Effectively, these are the system dynamics, the model of your system. In one of the lectures, we were discussing about the lower level of requirement, which is satisfying the physical reality. So this is what we do there. We know that in reality things can only act and behave in this particular way, so we include that as an equality constraint. These are inequality constraints on the system states, for example, an overshoot or a particular position that you want to avoid. And these are the inequality constraints on the control action, for example, actuator limits. So in linear MPC, by the way, in the optimization problem that I showed earlier, we have all the ingredients we need to be able to solve this problem. So A and B are the system state space model matrices, which we should have. Q, R, and P are so-called weights, and these are actually tuning parameters that you can choose. These are normally diagonal matrices, and there are a very good way of choosing P wisely. N, which is the prediction horizon, see how many steps we're going to look into the future, is also a parameter, and it's a trade-off. The more we look into the future, the better we can control. But of course, the optimization problem becomes larger, and it might be more difficult to solve. In reality, again, there are very good practical methods to decide what an acceptable number of steps to look into the future is. So how do we actually implement MPC? So what we do is that we measure or estimate the system states. So these are the outputs of our system. We solve the optimization problem. We put the output of our system in the optimization problem that we saw earlier, and we solve it. And there are very good solvers to deal with it. So we take the solution of this optimization problem, which is a trajectory into the future, and we only pick up the first control action. We apply the control action, and then we solve this problem again. And because we solve this problem again, MPC is often also referred to as the receding horizon control, because we look n steps into the future and we keep receding that horizon. When should we use MPC as compared to many other control techniques that you can choose from? I would say that MPC is particular. Well, MPC can do two things: can regulate, can bring a system to a particular state, or can generate trajectory. So that's one thing you need to think about. But I would say that MPC is particularly suitable when you have control techniques where you have constraints and you have more than one input and an output. It's true that you can clip input constraints. For example, if you have actuator limits, you can simply use a PID controller and then saturate the control limit. But as soon as you saturate, you realize that you're not behaving optimally anymore. Can MPC run in real time? I would say that very often these days, this is the case. This is thanks to the progress that's been made in algorithms development, so thanks to the mathematicians who are able to find better and better way of solving the optimization problem, but it's also thanks to better and better hardware implementation. So rather than using a generic method, you can specialize more to the particular hardware you're using, to the particular structure of the problem. There is a lot that is being done to make MPC run in real time. So megahertz rates are not unusual, especially for the linear MPC case. Things can become more complex. You could have a nonlinear objective function, highly nonlinear system dynamics. Things can be a little difficult there, but with careful selection and implementation of certain algorithms, I would say that yes, in a lot of practical cases, MPC can now be solved in real time. What is the difference between MPC and dynamic programming? Right, so they are both methods to compute optimal feedback control laws. So in this regard, they do the same thing. But this is the difference. So MPC uses an online optimization to solve an open loop control problem, and then the feedback control law is defined implicitly by repeating the optimization calculation after a feedback update of the state at each sample time. So that's how MPC work. Dynamic programming, on the other hand, derives an explicit feedback law offline by deriving and solving the so-called Bellman's optimality equation. So I think this is a good definition. It's not comprehensive, so if you're interested in this, go and find out more. What is the difference between MPC and reinforcement learning? So reinforcement learning is a model-free and adaptive method. So the system model is kind of learned online. It's not explicitly given a priori. Reinforcement learning has actually a lower online complexity than MPC, so it could actually be faster in certain cases. But reinforcement learning is nowhere near as mature as MPC in terms of stability guarantee, constraint handling, and the general robustness of the method. The fact that you're learning the model online has some advantages, but also can make things less suitable for safety critical application. So the lack of robustness is what makes reinforcement learning a technique that is inferior to MPC for safety critical applications. Okay, so this is what I want to say. I would say the takeaway point from this short talk is that you should use MPC when you have constraints and multiple input-outputs, and also remember that MPC can be used in two ways, either as a regulation problem or as a trajectory generation problem. So MPC is actually particularly useful for trajectory generation, and at the end MPC ends up in the solution of an optimization problem. So it takes some knowledge and understanding to transform an MPC problem into an optimization problem, and it takes a lot of effort to actually solve the problem, but luckily there are a lot of solutions already out there, and some of the free available solvers are extremely powerful. So don't be afraid to use MPC. Learn how to set up, and then go and find the best solver for your particular problem. Okay, I really hope I'll find the time to deliver another lecture on model predictive control with a lot more details and depth. In particular, I would like to concentrate on nonlinear model predictive control for the purpose of trajectory generation. I think such technique is so fundamental for the problem of motion planning, and I really don't see any other way of achieving high-level reliability and possibly certification unless we use physics and model-based methods like predictive control. I've got one more lecture I want to record now. It's going to be a short one, and it's going to be about an application of nonlinear model predictive control for motion planning, which I found particularly interesting and insightful.
In this video, we are going to demonstrate how to test the MPC for the trajectory tracking with the LGSVL simulator in Autoware.Auto. First of all, we assume that you have already done the whole setup of ADE and the LGSVL simulator. How to set up is described in the documentation. Okay, so let's get started. So currently in Autoware.Auto, we use the external MPC project, and it is included in Autoware.Auto as a subtree. So go to GitLab and go to that subtree, and you can see the URL of the original MPC source code. So go to this link. Here is the original source code of the MPC. So for the demo, I'm going to start the ADE at first. Go to the LGSVL documentation and copy this command to enter the ADE. Paste it. It's going to take for a while. So when you run the LGSVL simulator in the ADE, you need to pass the special configuration file to the ADE. That is the .aderc-lgsvl. Okay, so I'm going to enter the ADE in other terminals. And change directory to the Autoware.Auto and source install setup bash. Okay, so it's ready for the simulation. Then launch the simulator, go to the documentation, and copy this command. Now run it. And after this screen comes up, access to the local setup page described here. Click this one. So if setup is already done for the LGSVL, you can see some simulation scenario here. So click it and run it. Okay, so it's ready. Then this time we're using the map of the Automonasta parking lot. Okay, next. So this time we are going to use the MPC with the test package called the test trajectory following. So we're gonna run this command to test the record and the replay function. In this test, we're gonna move the vehicle manually at first in the simulation while recording the vehicle position and the velocity. After that, we're gonna replay the motion of the velocity with trajectory tracking using the MPC algorithm. So with this command, mainly 3 nodes are launched like this. So the record replay planner records the vehicle position and velocity and generates a trajectory from the recorded data. And the LGSVL interface is connected to the LGSVL simulator and publishes 2 messages, which are vehicle motion data and vehicle position data. The MPC with trajectory and motion data and vehicle position calculates the vehicle command, which includes acceleration command and steering angle command. So go back to the documentation and run this command. Then you're gonna see the RBs like this with the vehicle model and point cloud sensor data. So then go to the documentation. So in the record and replay, there are 2 options with joystick and with terminal. So this time use the terminal option and send a record action like this. Okay, so move the vehicle with the key cursor with your keyboard. And the vehicle position and the velocity are recorded to generate a trajectory. The feedback current length shown in the third terminal is the number of the trajectory points, and the default interval length between each point is 1 meter, so this means that the recorded trajectory length is about 500 meters. Okay, so I think it's enough. Then now I'm here, so stop the record, then go back to the start position. Just put the F12, then jump to the initial position in the LGSVL simulator. Then send a replay action with this command. Then you can see the recorded path is visualized on the RVs and the vehicle is gonna move. Okay, that's all. Thank you very much.
Hello again, everyone. This is the last of the series of lectures prepared and recorded for the Autoware Academy. In this last lecture, I want to show you a particular technique for solving the motion planning problem. I like this technique specifically because it kind of merged together some of the blocks that we saw in the previous talks, and it solves the problem almost in one shot. I think it's quite elegant and it's quite powerful, and yeah, I just want to share with you how this can be done. Okay, so we've been seeing this block diagram multiple times now, and I've been trying to convince you that this is a good way of splitting the motion planning problem or the decision-making problem into a sub-problem, into good, well-defined chunks of problem. But what I'm going to show you now is an advanced technique that integrates some of this block and try to solve the motion planning problem in a single shot. What's interesting to notice here that I draw this gray box cutting through the path planner and the controller, and there is a reason for that. For the path planner case, is because it's possible to include the path planner within the same problem and solve everything together, so that from the path planner all the way down to the control inputs. The problem is that this is still quite difficult, and it only works well in specific cases. Normally some sort of pre-processing is needed. On the other side, downstream, on the controller side, the reason is more practical. It is possible, given a fast enough implementation, which is, I know for certain that is achievable. Is it possible to control directly the low level, controlling directly the actuators of the vehicle? In practice, normally there are low level controllers which are well tuned, and there are other issues like going through certification processes. So it makes more sense to actually use the output of the motion planner, the trajectory, as a reference point, set points for the low-level controller to follow. But the main point being here is that the motion planning problem can be solved as a single problem. So the work I'm going to show you next is based on this paper. And what the authors do is that they show how to solve the path planning problem and path tracking problem as a single problem. Everything is framed as a nonlinear MPC formulation. So we've seen a little bit what MPC is. So this is a full nonlinear implementation because the vehicle model is nonlinear, and also because of the way cost function constraints are set up. For the case of where obstacle avoidance is needed, also some pre-processing is needed, and I will show you why that's the case. So let's remind ourselves why the motion planning problem is split into this sub-problem. There is a progression going from left to the right, so from upstream to downstream, that makes easier, and from the practical point of view, to split the problem. So if you remember, from the upstream, we tend to have slower updates. Timing is less of an issue. On downstream, on the other hand, updates tend to be faster. So this purely from the timing point of view. From the prediction horizon point of view, from looking into the future, upstream, we tend to look very much into the future. For route planner, actually, all the way to the goal state, while for the downstream, for the lower level part of the motion planner, short look ahead horizon are sufficient. Upstreams also we have low safety concern, while downstream safety concern are higher. Upstream, the problem is rather complex and therefore solved by heuristic algorithms, while downstream the problem tends to be a little bit easier, can be solved deterministically. So this is the reason why we break up the motion planning problem into sub-problem. But if you can somehow manage to achieve fast update, solve for long horizon, have high safety, requirements and solve the problem deterministic, in theory, it will be possible to do everything in one single shot. So I'm going to show what the guys in these papers do. Let's start from this picture here. So you can see these green dots representing the center line. Right, so what the center line is, in this case, it is not a traditional path to follow. It's more of a reference upon which progress needs to be made. So for the nonlinear MPC problem, the cost function is set up such that you try to maximize progress along this path. There is also a small cost that try to minimize the deviation from this path, but this is only a small cost that is put there as a technicality, because in reality we don't really care as far how far we are from the central path, as long as we are within the road boundaries. And to guarantee that the vehicle stays within the road boundaries, constraints are defined. And this is the second clever bit about the work that's been done here, is that constraints are defined as half planes for each individual point along the path. So you can see better from this picture that at each step into the future, there is a new set of half plane defining the constraints. Obviously, this is an approximation, but it works extremely well in practice, and it works also extremely well in terms of simplifying the problem enough to be able to solve everything in real time. So just to recap on this picture, we have these green dots representing the center line, red lines here represent the constraint, and what you see here defined as the orange dots is the actual trajectory calculated by the vehicle. So we saw that was the case without obstacles. If you now include obstacles, things become a little bit more complex, because inherently obstacles involve combinatorial decisions to be made, and also involve non-convex constraints. In this particular picture here, you can see that actually going past an obstacle could be done by going on either side. And this is not an easy problem for a nonlinear programming setup to solve. So what the authors of the paper do is to try to pre-process some information and overcome this issue. And the way they do it is that they superimpose a grid on what's happening in the future, so in the future drivable space. But the important point to notice here is that this grid is a spatial temporal grid. So these green dots that you see here are not only dots that exist in space, they also exist in time. So there is a picture like this for every time step that we have for future steps. The other interesting point here is that you can see this black line here, almost resembling a path, but in reality the pre-processing doesn't output a path. Instead, it outputs a drivable space, which is this gray area defined here. So in the pre-processing, we kind of block out certain area, as you can see on the outside of the red line, and we're effectively telling an MPC problem that anywhere within the gray area is a drivable space, and therefore it's possible to find a path through that. The reason why we have to deal with constraint this way is to effectively convexify the constraint, making the problem easier to solve. And here are some results of some simulation that are presented in the paper. So you can see here again the situation where there are obstacles, and the preprocessor defining this gray area, which is a drivable area, and then the path planning and path tracking problem solved in one single shot, and give it as a result this blue line here. And this is on the picture on the right is another step of the implementation. I've also borrowed some videos from the authors that can show on the left a simulation. So you can see actually here the vehicle running. You can see a line representing the center line, another line representing the path that is being, the trajectory, sorry, trajectory that has been planned. So I shouldn't make a mistake here. This is not just a path, it's a trajectory, so it's a whole set of acceleration, steering, and so on. And on the right, you can see the actual implementation of small-scale cars. The paper was actually developed for autonomous racing, but the technique is perfectly applicable to lane driving. So what are the main points to remember about this approach? Well, is that the motion planning problem can be solved in less steps. So obviously the splitting into chunks make the problem more manageable, but there are clever ways of reducing these steps and solving more of the motion planning problem into a single step. In this particular piece of work, path planning and path tracking was solved as a single problem. And in order to do that, you need the combination of two things effectively, a clever implementation of the problem and also an efficient way of solving the resulting optimization problem so that this can be implemented in real time in automotive grade hardware.
Hello and welcome to the Embotech lecture for the Autoware Academy. My name is Sandro Merkli and I'm a software engineer at Embotech in Zurich, Switzerland. In this lecture, we will see what the Embotech Autoware parking planner does, where it is in the repository, how to call it, as well as how to inspect the results visually. So stay tuned. The Embotech Autoware parking planner can plan parking maneuvers. In the graphic here, the aim is to plan a maneuver from a starting position here to an end position over here. And the blue rectangles that are shown here, here, and here are obstacles that are to be avoided. So now let's look at how this is done in software. In the following, we will assume that you have ADE installed, configured, and started in a fresh clone of the Autoware repository. If this is not the case yet, there are installation instructions available at the link that is shown here. For the purposes of this video, we will need to check out a demo branch because some of the functionality presented is not in the master branch yet. We will hence first add the Embotech copy of Autoware as a remote like so. Then we download all the branches from this remote using git fetch. And we switch over to the demo branch. Which is shown here. The final thing we need to do is update the submodules. Good. Everything is now ready for us to start looking at the parking planner. The code is in source motion planning parking planner, and it contains the same structure as all the other Autoware packages. Let's look at the interface to the planner itself. This is stored in the include folder in the main header of the parking planner. And the interface here is defined in a class that is called Parking Planner. This Parking Planner class has a constructor, which is shown here, which allows us to create Parking Planner objects with a given documented list of settings. After such an object has been created, we then call the plan method repeatedly to plan a maneuver from a given current state to a given goal state, avoiding a given list of obstacles. This function locks while a trajectory is being computed, and it finally returns with a planning result object. This object contains some meta information, such as whether the planning was successful, along with the resulting motion trajectory. In order to see a concrete example of how the planner is used, we can now head over to the tests and look at how it is done there. The tests are in a test folder
And the test of interest for us is in test integration. And here we want to look for a string called test p, which stands for parametric test. And here we are. Okay, so this is a parametric test that puts the planner through a variety of situations. In order to do so, one first constructs a set of lower and upper bounds on the vehicle state, a set of lower and upper bounds on the vehicle commands, and a set of weights for the optimization. Once these things are constructed, we can construct a parking planner object with all the settings, and after that we can call the plan method on this object. It's as easy as that. The rest of the code after this verifies that the results match the expected results, and it also does some plotting, which is helpful to look at the results and see whether they make sense or not. In order to see those plots, we will now have to go and actually build the planner and run the tests. This is done by first going back to the main directory and then running the build command. This command builds all the dependencies of the parking planner as well as the parking planner itself. Okay, and once this is built, we can go and run the tests, which is done using call const test packages select parking planner. Okay. This takes a moment because the parking planner is actually computing all these trajectories and it puts them in plots for us to look at afterwards. All right, there's a test failure here, but that is really only because of linting. The actual trajectory planning functionality is working properly. In order to now look at the figures, we have to go and install an image viewer in ADE because there isn't one at the moment as far as I know. We will do this with the following command. So we first get new package definitions, and then we install a package that is called EOG, which stands for Eye of GNOME. All right, with this installed, we can now go and look at the figures, which the test procedure has placed in the temp directory. We can do it like so, like so. All right, and now here we can see that for a variety of different maneuvers, the parking planner has successfully planned trajectories that drive from the starting position to the final position.
This concludes our lecture on both the practical and the theoretical part of what Embotech contributes to Autoware. I have shown you how to use the parking planner in isolation, and in the near future we plan on actually also integrating it with the rest of the simulation framework in Autoware. If you have any questions, you can always reach out to me on GitLab.
Fantastic, and I hope you found everything useful for my side. Again, if there is anything you'd like to ask, if you'd like to find out more, of course there is a lot more, feel free to contact me anytime. Thank you and goodbye.
Goodbye.